All right, it's been a little while. Let's go. Next unit, we're going to be talking about quadrilaterals, everything to do with quadrilaterals. We're going to jump right into it. This is the quadrilateral family tree. It's a little different than what you're probably used to. I'm going to start off by saying in our class, remember from first semester, we use what are called inclusive definitions. Inclusive definitions. Most people use what are called exclusive definitions. We don't use those. Let me give you an example as we go down here with trapezoids. So using inclusive definitions, we would say that trapezoids have, and this is a big deal, so first big deal, they have at least one pair of parallel lines. At least one pair. That is the inclusive definition. The exclusive definition would say exactly one pair. And that changes things quite a bit. On our tree here, this is where trapezoid goes. And notice that trapezoid leads to a whole bunch of other stuff. The reason being is because we're going to use inclusive definitions. That means it includes other things, such as parallelograms. So under our definition, parallelogram. Under our definition, a parallelogram is a type of trapezoid. Does a parallelogram have at least one pair of parallel lines? Yes, it does. So inclusive definitions means we're going to include more things, and that's the only kind of definitions that make a lot of sense at the highest levels. For instance, when you're in kindergarten, does it make a lot of sense to tell a kindergartner that a that a parallelogram is a type of trapezoid? No, you want them to be recognizing those as different and distinct shapes. But at the highest levels of math, parallelograms must be a type of trapezoid. It's the only way that the math works out. So we're going to be using inclusive definitions, and we're going to be learning all about all these parallelograms and rhombuses and all the different things. We'll go ahead and keep working on the trapezoid here for a second. So that's the main thing you have to learn. In every single shape, I'm going to put a big asterisk or star by the most important stuff that you need to know about that thing. And you got to get this stuff just on lockdown and quickly. So for the trapezoid, you need to know it has at least one pair of parallel sides. That has never happened before. That's the first time we have that in a quadrilateral. Now, if I number these angles 1, 2, 3, and 4, what are some symptoms or what are some things that are because the lines are parallel? Well, we know that the angles between parallel lines, so angles 1 and 2, and angles 3 and 4, we know that those are going to be supplementary angles. We know those are supplementary angles. So, for example, if this corner was 100 degrees, we would know that this corner is 80 degrees. Would we know anything about those two corners? No, not necessarily. Those being 180 have nothing to do with 3 and 4. Could 3 and 4 both be 90 degrees? Is that possible? Can a trapezoid have two right angles? Yeah, it sure can. It sure can. So angles 1 and 2 have nothing to do with 3 and 4. You can't go that way. No, 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 no. You can only work between parallel lines. So you can work with 1 and 2. You can work with 3 and 4. So not much to a trapezoid. You just have to know, hey, I got at least one pair of parallel lines. The next thing we're going to talk about is this guy over here called the kite. So if we move ahead to the kite, this one can be kind of tricky. But this is how I remember all the properties of a kite, is I know that a kite has what I'm going to call, or what is, a line of symmetry. It has one line of symmetry. So that's a big deal. And these are actual kites. Remember, they're not always drawn to scale, so, kind of be careful. But these are drawn to scale. So that horizontal line, that is the line of symmetry. How about on the other kite over here? Well, on the other kite, the vertical line would be our line of symmetry. So what does symmetry mean? It means that you have two equal halves or two equal parts. So here's what you need to understand, and here's what's going to help you solve problems that involve kites, is that a kite is simply when you take a scalene triangle. So like this triangle here, the blue triangle. If you take a scalene triangle and reflect it, you get yourself a kite. So what does that mean? Well, that means that these two sides would be equal, right? If it's a reflection. It means that these two sides would be equal if it's a reflection. If I call this angle 1, it would be equal to angle 2, right? If that's a line of symmetry, those two parts would have to be equal. Angle 3 would have to be equal to 4, and angle 5 would have to be equal to angle 6. So all of those are the result of this line of symmetry, right? We know that 1 and 2 are congruent. We know that 3 and 4 are congruent. We know that 5 and 6 are congruent. Those are all congruent pairs of angles. Couple other things, like if you look over here, if I were to draw the second diagonal, like what does it look like's happening? Well, if you said perpendicular, you are correct. So this is the main thing that is first introduced in the kite. You have to know this. The diagonals are perpendicular. That's never happened before. So if I'm like, hey guys, I got this shape. Its diagonals are perpendicular. What do you know about that shape? Well, you know that it is a kite. And going back to the tree, and you're going to have to get used to this. If it happens in a kite, let's actually fill out the whole tree real quick. We have kite. This is going to be an isosceles trapezoid. This is going to be a rectangle, a rhombus, and a square. There we go. Why were the 9th graders so sad? Because they got on the rhombus. Okay. But here on a kite, we have perpendicular diagonals. If it happens on a kite, it also happens in a rhombus and a square. There are 3 shapes that have perpendicular diagonals. But if the only thing you know is that it has perpendicular diagonals, what shape can you call it? Can you call that a square? No. No. It might be a square, but you can't guarantee that. I want you to look right here, guys. This is a shape with perpendicular diagonals. Is that a square? No. So just because it has perpendicular diagonals is not a guarantee it's a square. What is it a guarantee? It's a guarantee that it's a kite. But can it be a square? Yes. So if I said, hey guys, I got this shape I'm holding. It has perpendicular diagonals. Well, we would call it a kite. Well, what if it ends up being a square? Were we wrong when we called it a kite? No. Because based on the family tree, based on what we know about quads, kites can eventually turn into squares. Squares are a type of kite. So calling it a kite does not mean not square. And that's a big mental block a lot of people have to get over. Kite means it might be a square, but we don't know. But a lot of us in our head, when I call something a kite, we immediately think, oh, not a square. That's not true. That's going to get you in a lot of trouble. Kites might be squares. So you got to keep that in mind. Please, please, please. So here's the big thing, guys. The diagonals are perpendicular. It's the first time we ever have that. And that means we have right triangles. So when you have right triangles, you need to be thinking, ooh, you might be getting tricky with it. There might be sine, cosine, tangent. There might be 30, 60, 90s, 45, 45, 90s. There might be some Pythagorean theorem. All that's on the table anytime you have right angles. All right. Let's keep the ball rolling. Isosceles trapezoid. Isosceles, if you remember, means it has at least 2 equal sides. And those sides are called the legs. Now, at least 2 equal. Remember, we use inclusive definitions. So could this side also be congruent to the first 2? Yeah, it could. It might be. That's fine. Could this even be congruent? Now, this picture doesn't quite match it, but actually, yes. At that point, you're talking about a square now. But the 2 sides that are parallel are called bases. Right, so remember an isosceles triangle had 2 legs and 1 base, while an isosceles trapezoid has 2 legs and 2 bases. And just so you know, basically all these shapes that have parallel lines have bases. Parallelograms, these are bases, but these are also bases. So some shapes have more than one set of bases, but basically if you have parallel lines, you have bases. That's just the way it kind of goes. So these two parallel lines, these are the two bases. Now, we have some special properties. So we have legs are congruent. That's a big deal. It's not the biggest deal, but it's a big deal. Actually, I'm not going to put a star by it because it's not a huge deal, but a little dash maybe. And if I number these angles like 1, 2, 3, and 2, the foe. What can we tell there? Look real hard. We know these add up to 180. Yes, that's true. But that's not new. That's from trapezoids. We get that property from trapezoids. This is a type of trapezoid. So that's a property that's true for all trapezoids. I don't need to write that again. 3 and 4 add up to 180. True. Same thing, though. We already know that from the trapezoid. But what's new on an isosceles trapezoid? Well, the legs are congruent, but also angles 1 and 4 will be congruent. Angle 2 and angle 3 will be congruent. Two angles that touch the same base are going to be congruent. So what we say is base angles are congruent. And in this case, that would be 1 and 4 and 2 and 3. Those are congruent angles. So if I knew that this corner was 80 degrees, well, this has to also be 80. And this would be 100, and this would be 100. So on an isosceles trapezoid, you just need one corner to know all four. So those are congruent. Now, notice none of those are the big deal. There is one big deal that's never happened before, and it has to do with the diagonals. If I draw the diagonals of this trapezoid, I want you to look real hard. What do we notice about the diagonals? Now, you might think they're perpendicular. And on this example, they do look real close to perpendicular, but look over here. What if I draw the diagonals on this one? They don't look nearly as perpendicular, do they? So sometimes it does matter what kind. Like if you make a wider, bigger trapezoid, you might get some properties that are a little bit misleading. That especially happens like on rectangles. Like look at these two rectangles. This one looks like a lot like a square. And so if you just draw a rectangle that looks like a square, you might think you have properties that you really don't. Like if I draw the diagonals over here, let's just take a look at this real quick. This is like an extreme version of the rectangle. Versus the diagonals over here, there's a few things that you might notice. One, on the one that looks more like a square, doesn't that look really close to a right angle? It's not perfect, but it looks really close. But what about this long one? Does that look like a right angle? Nope. How about the corners? Do these corners look really close to equal? Yeah. How about over here? Do the corners look really close to equal? No. So if I'm trying to test the properties out on a shape, I'm drawing like an extreme longer version of the shape, not one that's more squared up and more equal dimensions. You got to be real careful about that. But going back to our isosceles trapezoid, the thing that is true is that they're the same size. So if I call this A, B, C, and D, what we know is that AC is congruent to BD. We do know that. So the big deal here is that the diagonals are congruent. That's never happened before. That's the new deal. All right, so let's go back up to the tree. This is stuff you're going to have to be doing. So here we have congruent diagonals for the first time. So if I say, hey guys, I got this shape. It has congruent diagonals. What would you call that shape? Well, that's an isosceles trapezoid. Now, there are three shapes that have those properties, but could you call it a rectangle for sure? No, you can't. Could you call it a square? No, you can't. But let's spice it up a little bit. What if I said, hey, I got this shape. It has congruent diagonals and perpendicular diagonals. So take it one piece at a time. Congruent diagonals, you know it has to be one of these three. These are the only shapes with congruent diagonals. And if that's all you knew, you would say isosceles trapezoid. But wait, what else they tell you? They tell you it also has perpendicular diagonals. So it has to be one of these three, but because the diagonals are perpendicular, it has to be one of these three. So what's the only shape that is in both circles? That's the square down here. So if I said, hey, I got a shape where the diagonals are perpendicular and congruent, you now know that you're talking about a square. Is that pretty cool? What if I said, hey guys, I got this shape. The diagonals are perpendicular, so now you know it has to be one of these three shapes. Those are the only three shapes with perpendicular diagonals. And it's a trapezoid. Ooh. Well, trapezoid is all of these. So where is the overlap? There are overlap in two places. So which shape do you pick? Do you call it a square or do you call it a rhombus? Well, you would have to call it a rhombus. Mr. Bannon, it could be a square. It could be a square, Mr. Bannon. I know. It could be a square. You're not wrong. But can I draw a trapezoid that has perpendicular diagonals that is not a square? And the answer is yes. It's called a rhombus. What if it ends up being a square? Were we wrong? Nope. No. A square is a type of rhombus. So we use inclusive definitions. That means when I say rhombus, I am meaning it's a rhombus, but it could also be a square. We just don't know that. So, like I said, a huge mental block that everyone has is that if I call it a rhombus, you immediately think, not square. Well, that's not true. Rhombus might be a square. So if it ends up being a square, we weren't wrong. What if I said sometimes, always, or never, a rhombus is a square? Sometimes. Sometimes a rhombus is a square. What if I flip the order? Sometimes, always, or never, a square is a rhombus. Always, every square is a type of rhombus. As a matter of fact, square is everything here. Everything in the map. A square is a rhombus, it's a rectangle, it's all of these things. Square is all of the things. All the time. All right. So let's keep the party going. We got parallelograms. There's a lot here. I'm going to go over these properties kind of quick. There are 5 of them. First, we have opposite sides are parallel. That's like the essence of a parallelogram. We have opposite sides parallel. We have opposite sides are congruent. So not only are they parallel, but they're also congruent. We have opposite angles congruent. So like if I have angles 1, 2, 3, and 4, we know that 1 and 2, we know that 1 and 3 and 2 and 4 are going to be congruent angles. So as a for instance, if I knew that this was 80 degrees, let's go a little bit bigger. Let's say that this one's 100 degrees, then this has to be 100 degrees. Okay, well, then we also know, this one's a little bit trickier, but because of the parallel lines, what do we know about the angles in between parallel lines? And because all the lines are parallel, we can even go this way. We know that in between parallel lines, they're going to be supplementary. We're going to call those consecutive. Consecutive angles are supplementary. What does consecutive mean? It means next to or the next one. So like if I'm standing here, like these are consecutive corners, 1 to 4 to 3 to 2 back to 1. Those are consecutive. Not going through the shape, that's not consecutive. 1 and 3 are opposite. It's like in baseball, when you're running the bases, as long as you're running them in consecutive order, you'll never cross like the pitcher's mound. But if you go, like from first base to third base, you cross like the pitcher's mound, that's not consecutive anymore. So as long as you're running the base paths, you're always doing consecutive bases. Consecutive is next to. All right, so what does that mean? Well, if those are 100, well, then these have to be 80. These have to add up to 180. 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 Any two consecutive corners have to add up to 180, and opposite corners have to be equal. And then the last one's kind of hard to tell, very hard to tell. But if you draw the diagonals, let's look at them. What do you think is true? Are they equal? Well, no, they aren't equal. Does this, look how long that is. Look how long, like those are not the same size for sure. But they do cut each other in half. So like if this is 10, then this would be 10. If this is 5, then this would be 5. So they cut each other in half. That doesn't mean they're equal, but they cut each other in half. That's the fifth thing. they bisect, the diagonals bisect each other. Woo! And then for the big time, if any of the 5 occur, guess what? They all 5 occur. So if any one of these things happen, you know you're talking about a parallelogram. You think that's ever going to come up? Absolutely. If you're working on a problem, like look at this picture. If this is all you knew, if you knew that the diagonals were bisected like this, that is enough to know it's a parallelogram. Now you know the opposite sides are parallel. So like if you knew this angle was 10 degrees, then whoop, this angle has to be 10 degrees as well because of alternate interior angles. So once you know one of the 5 properties, then you know all 5 properties have to happen. Let's go back up here for a second. What if I said I got a shape and the diagonals are perpendicular and they bisect each other? Well, here are perpendicular diagonals. Where do the diagonals bisect each other? What did we just say? That's right here on the parallelogram. The diagonals bisect each other. I don't want to write all that, but bisect each other. So that's all of those. So perpendicular diagonals, it's got to be one of these 3. Bisect each other, it has to be one of these 4. Well, this is the overlap. These 2 shapes, rhombus and square, have both things. They bisect each other and they're perpendicular. So you'd have to say rhombus. But what about a square, Mr. Man? I know, I see the square. A square is a type of rhombus. So if I say rhombus, I am including square. But if I say square, it means I can guarantee you it's a square, and we can't do that. I can draw a shape where the diagonals bisect each other and they're perpendicular, where it's not a square. I can do that. But I can't draw that shape and it not be a rhombus. It must be a rhombus for all that to happen. So you have to figure out which shape it must be. What if I said, hey guys, I got a shape. The opposite sides are parallel. So you know it's one of these. These are the shapes with parallel sides. And the diagonals are congruent. Well, here are the shapes where the diagonals are congruent. So what would you have to call it? You'd have to call it a rectangle. What if I said sometimes, always, or never? These get a little trickier, maybe. A rhombus has congruent diagonals. Sometimes, always, or never, a rhombus has congruent diagonals. Well, here are my rhombuses. So I know it's got to be one of these 2. Do either one of those have congruent diagonals? This one does not, but here are my congruent diagonals. This one does. So does a rhombus always have congruent diagonals? No, I can draw a rhombus that doesn't have congruent diagonals. So my next question is, does a rhombus ever have congruent diagonals? And the answer is yes. A square is a rhombus that has congruent diagonals. So sometimes, always, or never, a rhombus has congruent diagonals. The answer is sometimes. When? When it's a square. All right, moving on. Here's my rectangles. You know, if you go to some guy on the street and you say, what do you know about rectangles? They might tell you a few things, but you hope they remember its main property, and that is all angles are congruent. They're 90 degrees. That's the main thing. Now, there's some other stuff that goes on, but the angles must be 90 degrees. All right, let's say I have A, B, C, D here, and they tell you that AC equals 10. AC equals 10. What else would you know if AC equals 10? Well, you know because that it's a parallelogram that the diagonals bisect each other. So this would be 5 and 5. You know because it's an isosceles trapezoid that the diagonals are congruent. So you would know that DB equals 10 as well, making this also 5 and 5. So because they told us AC is 10, we know all this stuff. And I did that for a reason. What kind of triangle is this green triangle? The diagonals bisect each other and they're congruent. So what you end up making are little isosceles triangles. So like if this is a 70-degree angle, then this is also 70 degrees because of that isosceles triangle. You know the entire corner is 90. So if that's 70, this would be 20 and this would be 20. We can get the other ones a few ways, like wouldn't these be alternate interior angles, right? So these two spots would be alternate interior. Or don't you have another big isosceles triangle here? So if that's 20, then this would be 20, making this 70, making this 70, making this 20. So, and then using our triangle rules, right? Like look at this isosceles triangle, 70 plus 70 is 140. So this would have to be 40. Which means this is 140, 140, and this is 40. So just knowing one angle, let us fill out every angle in the picture. Now this will be on tonight's assignment. What if I called this side X and asked you to solve for AD? What if they said AD equals something? We want to know what AD equals. Well, we know we have right triangles. So I would focus my attention on right triangles. So if you look at this black right triangle, what we basically have here is X over here. We know that we have 70 at the top, and we know that the hypotenuse is 10. Right? Isn't A to C 10? So now this is a problem from last chapter, right? If we have a right triangle, this would be adjacent over hypotenuse. So this would be the cosine of 70 equals X over 10. So it'd be 10 cosine 70, whatever that is. And you're going to have to do stuff like that. You're going to have to do stuff like that. All right, let's go look at the rhombi. Rhombi is plural for rhombus. Rhombuses is also a word, no big deal. So we got some stuff. I'm going to go kind of quick through this, but remember that a kite has one line of symmetry. Well, guess what? A rhombus has two lines of symmetry. So going back to the kite real fast, a kite is when you take a scalene triangle and reflect it. A rhombus is when you take an isosceles triangle, right? Like if these two sides are equal and you reflect it, now all four sides are equal. That's big property number one. Four congruent sides. So that's a big deal. We have four congruent sides. Also, 1 and 2. What do you think is true about those two angles? Right, they're equal. 3 and 4, also equal. 5 and 6, also equal. 7 and 8, also equal. So what we say is that the diagonals bisect the vertices. So it folds in half. If you think of it as folding, wouldn't the left side also fold over to the right side? Yes. Yes, we have two lines of symmetry here. So those are the new properties that the rhombus introduces. We also know that we have 90 degrees here in the middle. So here's an example. Let's say that we know that like this is 30 degrees. Oh, you love seeing 30. I know you do. What would we know? If that's 30 degrees, we would know this is 30 because we know it's folded in half. We know that those corners are cut in half. It's a parallelogram, so we know that opposite angles are the same size, so those are also 30. This whole corner is 60. That means this whole corner has to be 120, which means it has to be a couple of 60s, or you could have known that it's a 30, 60, 90 because the middle angles are 90 degrees. So once again, if you just know one corner of a rhombus, you can fill the whole thing out. So what if I told you this side was 12? Could you find the area of the rhombus? So this is what you'd have to do. Like you see this triangle? We got a right triangle here. This is a 30, 60, 90 with a side of 12. Divide by 2, this would be 6 times root 3. This would be 6 root 3. So it'd be 1/2 times base times height. That's one triangle, and then there'd be 4 of those. So yeah, We could get the area of that rhombus using our 30, 60, 90 rules, or it might be a trig like sine, cosine, tangent. There's all kinds of stuff that you can try to figure out there, or that you can use. All right. I'm feeling pretty good. And then let's take a look at squares. Nothing new. Other important characteristics. Every property listed. The square is everything we've talked about so far. So let's repeat them, and I hope you can try to repeat them as well. You can pause the video if you need to, but let's go through the list. We start with a quadrilateral. What does a quadrilateral introduce? And I forgot to mention this actually. Quadrilaterals are 4 sides and they're 360 degrees. So a square has 4 sides and 360 degrees. Then we went and talked about the trapezoid. A square has at least one set of parallel sides. Yeah, actually they're both parallel, but it has at least one set. Then we went over to the kite. On a kite, we got perpendicular diagonals. Then we went over to the isosceles trapezoid. We got congruent diagonals. Then we went to the parallelogram. Then we got diagonals that cut each other in half. So not only are they congruent, but they cut each other in half. So all those parts are equal. We got opposite corners equal. We got opposite sides equal. We got diagonals that bisect each other. We got consecutive corners that add up to 180. Then we went over to the rectangle. We learned that all the corners have to be 90. And then we went to the rhombus and we realized that all the sides have to be equal. And the corners are cut in half. So if they're all 90 and we cut them in half, now they're all 45s. So we have a ton of 45, 45, 90 triangles here. And we use the best one. So like if I knew that this side was 10, I would use this big 45, 45, 90. I would know that this is 10. I would know that this whole thing is 10 root 2. That means these little parts would be 5 root 2 each. If I knew that this little part was 10, I would use like this little 45, 45, 90. This would have to be 10, and this would have to be 10 root 2. There's lots of ways to solve them, but we know that we're working with 45, 45, 90s. Nice. A couple other things before we go. I mean, that's the main stuff here, guys, but like talking about a kite, can a kite have exactly one right angle? Well, let's say that this was 45. This is 55, and this is 80. When you reflect it, this would be 45, 55, and 80. Remember, a kite has one line of symmetry. Well, how big is this corner now? It's now 90. So you'd have a 90, a 110, 80, and 80. So yeah, a kite can't have exactly one right angle. Can a kite have exactly 2 right angles? Well, could this corner be 90? And then you reflect it, and this corner would be 90? Yeah. And then these could be any other number? Yeah. So yes, you can have exactly 2 right angles. Can you have exactly 3 right angles? So let's say that this is 45, which would make this whole corner 90. Let's say that this is 90 and 90. What would be left over? Well, if 3 corners are 90, this corner would have to also be 90, so no. So you can't have exactly 3 right angles. That's actually not possible. If you have, sorry, you can't have, what did I say? You can't have exactly 3 right angles. If you have 3 right angles, you are guaranteed to have 4. How about on a trapezoid? Can you have exactly 1 right angle? Look at this trapezoid. Can just one of these angles be 90? So let's say this one's 90 degrees. Well, because these are supplementary, this is also 90. So can a trapezoid have exactly 1 right angle? Nope. Can it have exactly 2 right angles? Yes. How about 3? No, none of them can have exactly 3. So that's the kind of thing you have to do, guys. You're going to have to plug in numbers, test things out, see how they work. You're going to have to do trig, Pythagorean theorem, 45, 45, 90s. There's a lot to know and do here. You need to know all these properties, especially the ones I put an asterisk by. You need to know how to move up and down the tree. You need to know how to recreate the tree, right? So Every single, it's the new SOHCAHTOA. You have quadrilaterals, go to trapezoids and kites, goes to isosceles, trapezoids, and parallelograms. Those two make a rectangle. These two make a rhombus, and rhombus and rectangle make a square. You need to be able to make that quickly. So when I ask you questions that refer to properties, you can know how they're related. So like if I say, hey, I got a shape where the diagonals are perpendicular, you know it's one of those. And the opposite angles are congruent, so you know it's one of those. Because you need to know the first time it happens, you need to know every time it happens. So like diagonals perpendicular happens in a kite, that's the first time, but it also happens in a rhombus and a square. The opposite angles are equal, that happens in a parallelogram. It also happens in a rectangle, rhombus, and square. So if I said, hey, I have diagonals that are perpendicular and opposite angles are equal, you would know to call that a rhombus. That's the first time that those two properties happen. Having this tree is the new SOHCAHTOA. You need to have it. You need to use it. You need to know where all your properties are. The parallelogram has a bunch. That's where a bunch of them are located. Now would be a good time, maybe from memory, right now. See if you can write down what happens in all of these shapes. I'm going to verbally go through them again right now. So, 4 sides, 360 degrees, quadrilateral. Trapezoid, at least one set of parallel lines. Kite, diagonals are perpendicular. Isosceles trapezoid, diagonals are congruent. Parallelogram, big list. See if you can write these down before I say them. But diagonals bisect each other. Opposite sides are parallel. Opposite sides are congruent. Opposite angles are congruent. Consecutive angles add up to 180. There are 5 things that you need to know there. And if any of those happen, they all happen. Rectangle, all 4 corners are 90 degrees. Rhombus, all 4 sides are equal and all 4 corners are cut in half. The diagonals bisect the vertices. And then square, nothing new, but it has every property we just said. So knowing when these properties occur is a big deal. You need to get that down. You need to have it down pretty much immediately, my friends. All right, have fun.